This video will continue to talk about the brain mechanisms of movement. We'll move on from the primary motor cortex and into the cerebellum. So just to remind ourselves of where the cerebellum is, it's back here, sitting behind the pons and the medulla. And again, we'll see that the cerebellum has more cells than the rest of the nervous system combined. So it's got these very densely packed neurons. And we only really talk about a few roles that the cerebellum plays. So I really feel like we're just kind of scratching the surface. But today we're going to talk about its role in movement. So think back to our anatomy chapter. What did we say about the cerebellum? What did we say was the role of the cerebellum in movement? Hopefully you're remembering balance and coordination. So the cerebellum is going to help that gymnast walk across that balance beam. The cerebellum is going to help that softball player aim that softball and strike out the next batter. So the cerebellum is important in, it's not issuing orders to the muscles, it's helping coordinate those. So when the motor cortex sends those orders down to the motor neurons and the interneurons, it also sends a copy of that information to the cerebellum so that the cerebellum can coordinate those movements. So it's important in movements that require aim, timing, and rhythm. So in terms of rhythm, think about things that, like clapping your hands. When you clap your hands to a beat. Speaking, there's definitely a rhythm to speaking when you're writing things down. Really anything that involves aim. I was watching something one time and it said that, the cerebellum was involved with all sports that involved aim. And then I tried to figure out a sport that didn't involve aim. I mean, you think about archery involves aim. Swimming involves timing, right? So that's definitely not aim, but baseball, softball, they all seem to involve some sort of rhythm or timing. So the cerebellum, to me, I can't think of a sport that it wouldn't be involved in. So this next little cartoon is just to help you remember what I was going to say next, and maybe to help you remember the role of the cerebellum. So here you see a police officer, and he's pulled this guy over and is doing a sobriety checkpoint test. And he says, actually, I wanted you to touch your own nose. And so you see the drunk guy is touching the police officer's nose. And that's because one of the things the police officers are testing when they do those field sobriety tests is if your cerebellum has been impaired, because the cerebellum is one of the first areas that's impaired by alcohol. And so that clumsiness or loss of balance that you may experience when you've had a little too much to drink, or you've seen your friends experience when they've had too much to drink, that's the same type of clumsiness that you would see in someone who actually had damage to their cerebellum, whether it would be a stroke or some sort of blunt force trauma or tumor or what have you. The police officer might also ask you to follow a finger or a pen light with your eyes, and what they're looking to see is your eye movements. Are they shorter or jerkier? Are they moving from spot to spot? That's called the Saccadi's eye movements, and so that also would be impaired with cerebellar damage. So people with cerebellar damage would also have trouble playing most sports that require, like I already said, sports that require aiming or time, but activities like playing an instrument, dancing, where you said clapping hands, anything that really involves rhythm, the cerebellum is very important in. And as I said before, the cerebellum has more neurons than all other brain areas combined, which again, I think we're just kind of scratching the surface of what the cerebellum does. We know that it seems to be important in some aspects of attention, shifting our attention. I saw a newer study that came out that said that it perhaps has a new reward system that the cerebellum is involved in. We spoke in the last chapter about the role of the cerebellum and that lateral inner positive nucleus in classical conditioning. So the organization of those cerebellar cortex neurons allows this control of these precise timing, aim, rhythm, balance, and coordination. It has a very precise geometrical pattern. So there are Purkinje cells, and these Purkinje cells are flat cells that are in sequential planes. So hold up your hand and think of the palm of your hand as being the cell body of that Purkinje cell, and think of your fingers as being the dendrites that receive that information, and your arm as being the axon. And if you're holding it up as kind of a 90-degree angle, and then line up another one that's right next to it. Not in front of it, but next to it. And that's how you have these rows of ththese Purkinje cells. And then they're innervated, so they're flat parallel lines in sequential planes. And then they're innervated by parallel fibers. So now put your hand back up, and again, those at a right angle, and those fingers are receiving information. And now take your other hand and put your fingers in at a perpendicular angle. So now they're crossing, they're intersecting. And those fingers from your other hand are like those parallel lines. So the parallel fibers, they're axons that are parallel to one another, and they're perpendicular to the planes of the Purkinje cells. So the cerebellum receives input from the spinal cord and each of the sensory systems and the cerebral cortex, and sends it to the cerebellar cortex. So the cerebellar cortex is going to be that surface of the cerebellum. So the greater number of excited Purkinje cells, the greater their collective duration of the response. So here's what I was talking about. So again, here's the cell body of that Purkinje cell. Imagine that being your palm. This is your arm going down. Of course, instead of bending at your elbow, it continues to go down. And then those fingers are these very elaborate dendritic arbors that the Purkinje cells have. Now these parallel fibers, they come up from the granule cells. And again, they're coming up and they're running perpendicular to these planes of Purkinje cells. And it's believed that this geometric pattern and the way that the parallel fibers innervate these Purkinje cells is what allows for the precise timing of movements. Now, we already mentioned the cerebellum does have some other roles. We talked in the last chapter about its role in classical conditioning, specifically that lateral interpositive nucleus. We know that it's also involved in attention. People with cerebellar damage have problems in shifting their attention. And again, newer research suggests this reward response. Perhaps the granule cells in the cerebellum, they were able to alter them so that they would light up with fluorescence whenever active. And they were giving sugar water to the rats and have them press a lever. And they thought the cells would light up with movement, but they also had a response to ingesting the sugar water. And the sugar water is like a reward. And so we'll talk later in the semester about the reward system with the nucleus accumbens and the VTA, but this is another area, and just kind of suggesting that perhaps there's multiple overlapping reward systems in our brain, and probably for a good reason.